Hello and welcome everyone to LFI Educates. Today we are continuing with this chapter, chapter 12, that is atoms. The first thing that we are going to learn today is about the basic postulates or Bohr's postulates. Bohr's postulates of the atom, the structure of the atom. The first point is said like this: the electron revolves around the nucleus in a fixed circular orbit. This is the first postulate. The electron revolves around the nucleus in circular orbits. This is the first postulate. That means the path in which the electron revolves around the nucleus, it is circular. It is circular, he said. Then the second thing, the second postulate, what he said was the orbit in which the electron revolves can take only some special values, can take only some special values of radius. Their radius are fixed. The first orbit that will go around the nucleus, suppose this is your nucleus, this radius it is fixed. First orbit, second orbit, again the radius are fixed. In this orbit of special radius, the electrons does not radiate energy. That means when the electron revolves in the special orbits, they do not emit energy, they do not radiate any energy as expected by Maxwell. Or as expected by Maxwell's laws. And these orbits are also known as stationary orbits. These orbits around which the electron revolves around the nucleus are also known as stationary orbits. These orbits are also known as stationary orbits. This is the second postulate given by Bohr. In the third postulate, he said that as long as the electron revolves in a particular orbit, it does not emit or it does not absorb any energy. As long as the energy of an electron in a particular orbit is fixed. But if an electron undergoes transition from lower energy state to higher, or from higher energy state to lower, then it will emit radiation or it will absorb energy. But if an electron transition means the change in orbit by the electron takes place it will either absorb energy or radiate energy in the form of photon. Either it will absorb or it will radiate energy. If the electron transition takes place from higher energy to lower energy, says like this, mathematically E, that is equal to your h nu, that is EI minus EF. If EI, initially this energy is higher, from higher to lower, then I indicates the initial and F indicates final. Energy in the initial state, if it is higher than energy in the final state, then that means the electron is jumping from higher to lower energy state, then energy is emitted. It will emit energy in the form of photon. And if final energy is more, if the initial energy is less and the final energy is more, that means if an electron jumps from lower energy state to higher energy state, then energy is absorbed. This is happening in our day-to-day life. All of you know electric bulb we have seen. When we are applying electrical energy to the bulb, then what is happening? The electrons, they are jumping from lower energy state to higher energy state. They are absorbing energy. But to become steady, they fall back again from higher energy state to lower energy state. In that process, it gives us light, that we call it as photon. And to measure this photon, this one you know very popular, you have already done with this. E is equal to h nu, that is hc divided by lambda. This is the energy of a photon given by Max Planck. H is Planck's constant, nu is the frequency of radiation, c is the speed of light, and lambda is the wavelength of light or wavelength of radiation. This is the third postulate given by Bohr. Now let us see the most important one. I cannot say the most important one, this one is also equally important. But the fourth postulate, it tells us about the quantization of angular momentum. Bohr said that only those electrons can revolve in a particular orbit if the angular momentum of the electron is equal to the integral multiple of Planck's constant divided by 2 pi. It says like this, only those electrons can revolve nucleus in a particular orbit if its angular momentum let us write it as L, small l or capital L you can use, is equal to an integral multiple of Planck's constant divided by 2 pi. If they are not equal, very sorry to say that they cannot revolve in a particular orbit. It says that the angular momentum and this value all are constants here, where n is a principal quantum number, n takes the values 1, 2, 3 and so on. Depending upon the orbit, you number it, first one, second one, third one, fourth one and so on. The angular momentum, how do you calculate? You have your formula mvr, n times h by 2 pi. If it is equal to these two values, then that particular electron can revolve in that particular orbit. So this one you have to calculate separately. And this is which orbit you are talking about. If first orbit you put n equal to 1, these are constant values. H value is 6.626 in 10 to the power minus 34. But you can take 6.63 as well. If you round off to 2 digit after a decimal. And pi, you know all of you, 3.14 or 22 by 7. Multiply, you get one value. Then this value also you have to multiply and see. You will come. Then velocity, with which velocity the electron is revolving, the velocity vector, and the mass of electron is fixed. That value if you multiply and this value if it matches, then we can say that this electron can revolve in this first orbit if I take n equal to 1. If I take n equal to 2, then the story will be different. The electron velocity will be different, radius will become different, mass will remain the same. Then you will calculate it. Then here n will be equal to 2. Then match it. If they are equal, then yes, that electron can revolve. If not equal, then that electron cannot revolve in that particular orbit. This fourth postulate is also known as I said to you earlier, the quantization. This is Bohr's quantization condition also we say. This is Bohr's quantization condition. This we call it as Bohr's quantization condition as well. These are the four basic postulates given by Bohr. Let us see Bohr's theory of hydrogen-like atoms. Here hydrogen-like atoms indicates even for lithium as well as helium, but in the ionic state their number of electrons must be 1, then it is applicable. Now in this case, let us assume that this is the nucleus plus Ze, the charge, and according to Bohr, the electron revolves around the nucleus like this. Linear velocity will be tangential with the orbit. This is the radius r, and mass of the electron, let us take it as m. To start this way, that E M and V be the charge, mass and velocity of the electron respectively. Then let r be the radius of the orbit. Also let r be the radius of the orbit. In this case, if a body is revolving around the circular path, we all know that it will have centrifugal force, that is Fc. This centrifugal force Fc is provided by the electrostatic force of attraction between the electron and the nucleus. So we'll write like this: the centrifugal force is provided by the electrostatic force let us write Fe. Centrifugal force Fc you can write. It's provided by the electrostatic force between the proton and between the electron and the nucleus. Therefore, centrifugal force must be equal to the electrostatic force. The expression for centrifugal force, that is mv square divided by r, that is equal to the electrostatic force, it is Coulomb's force, 1 by 4 pi epsilon naught, charge of electron, charge of nucleus, the product divided by the distance, that is r square. One r you can cancel it out here, and then you can write this as mv square is equal to 1 by 4 pi epsilon naught z square. You can write here z square divided by r. Let us mark this as equation number 1. Now, by Bohr's quantization condition, or from Bohr's quantization condition, we know that angular momentum is an integral multiple of nh divided by 2 pi. Angular momentum is mvr, that is equal to nh by 2 pi. From here, temporarily you can find out the value of v, that is nh divided by 2 pi mr. So mr will come down. Let us mark this as equation number 2. So if you put the value of v from equation 2 in equation 1, you will get the expression for radius. Putting the value of v from equation 2 in equation 1, we get here m v square, means this one v, we'll put whole square, m v square, then will be n square, h square, all the terms square. 2 square is 4, pi square, m square, r square is equal to z square divided by 4 pi epsilon naught r. Z square divided by 4 pi epsilon naught r. Then one r you can cancel it out. Then this m and all will cancel at the end. This, what is this value of r, we'll find out. R is equal to, all the terms will be up, 4 pi epsilon naught m n square h square divided by, here you will have 4 pi square m square, this r you have written here, and then z square. Then you can cancel it out. 4, 1 pi will get cancelled, mass, one term will get cancelled, and nothing more than that. Now R is equal to 4 got cancelled. This is epsilon naught n square h square, or we can write n square epsilon naught h square divided by pi m z e square. Pi m z e square. This expression gives us the expression for radius of the orbits. This is equation number 3. I'll write down. Equation 3 is the radius expression, is the expression for the radius of the orbits. If it is the first orbit, we will put n equal to 1. If it is second orbit, n equal to 2. If it is third orbit, n equal to 3, and so on. Now here, in a short way, you can learn like this. R is directly proportional to n square. These are all constant terms. You can see very carefully. Epsilon naught, permittivity in free space. H is Planck's constant. Pi is constant. Mass of electron is constant. This Z, atomic number for a particular electron, will be constant. E, the charge of electron, is constant. So like this, we'll get it. This is very important relation we have to remember while solving the numericals. Question 4. This also shows that the radius of the orbits are in the ratio n1, 1 square is 1, n2, 2 square is 4, n3, 3 square is 9, n4, 4 square is 16, and so on. The ratio of the radius are in this order. That clearly shows that if this is the nucleus, the first orbit, if it is at 1 centimeter, the next orbit will be 2, 1, 2, 3, 4 here. So the radius are not equally spaced. Next will be 9, up to here is 4, 5, 6, 7, 8, 9 here. Like this, the radius are spaced, that you come to know from here. That means the radius are not equally spaced. This shows that the radius are not equally spaced. You can put full stop and write the radius are not equally spaced. Now for hydrogen atom, let us see. This is in general we have done for all the atoms. Now for hydrogen atom, we know that it has only one orbit, n is equal to 1, z is equal to 1. Atomic number is also 1. Put it in equation 3. You will get R is equal to epsilon naught h square divided by pi m e square. This expression is known as Bohr's radius also. This is known as Bohr's radius, and he even calculated this value as well, because all are constant terms. On putting the values or on calculation, Bohr found out that R, the radius of the hydrogen atom, is 0.53 angstrom unit. So from this value, what you can understand is, first orbit number 1 is at 0.53 angstrom unit. Second orbit will be where? Then 4 times this one, 0.53 angstrom unit. Next one, 9 times 0.53 angstrom unit, and so on. So like this you come to know about the radius of the orbit. Now let us see the expression for velocity. In stationary orbits, let us see the expression. To get the expression for velocity of electron in the stationary orbit, we will take the Bohr's quantization condition from Bohr's quantization condition. Angular momentum is equal to n times h by 2 pi. Angular momentum is mvr, is equal to nh by 2 pi. Then value of v will be nh divided by 2 pi mr. After getting this, put the value of r that you got it earlier. Putting the value of r, you got like this: n square h square epsilon naught divided by 4 pi z m e square. This is the expression of r, the radius of the orbit. In this equation, let us mark this as equation 1. In equation 1, we get v is equal to nh divided by 2 pi m. R value, if you put it here, it will be n square h square epsilon naught divided by, it will come up pi z m e square. And if you cancel the terms that are available to you, nh one time you can cancel it out, pi you can cancel it out, then you get the expression like this: v is equal to z, this m also will get cancelled out, z e square divided by nh 2nh epsilon naught 2nh epsilon naught. This expression will give you the expression for velocity of electrons. Let us mark this as equation number 2. Equation 2 is the expression of velocity in the stationary orbits. Now, to get the expression for Bohr's velocity for hydrogen atom, if you do for hydrogen atom, z is equal to 1 and n is equal to 1. So, velocity for the electron in the first orbit you can calculate like this: e square divided by z is 1, n is 1, so it will be 2h epsilon naught. And Bohr calculated the velocity, this one, as c, the speed of light, divided by 137. After putting all the values, it was equivalent to this value, where c is the speed of light, 3 into 10 to the power 8 meter per second in vacuum or in air. And this way he calculated the velocity of hydrogen atom. So from here what we learn is, from equation 2, what we know is velocity is inversely proportional to the number of the orbit as you go away from the nucleus. Suppose this is the nucleus, first orbit, second orbit. The velocity of electron here, if it, n is 1, here n is 2. If it is 1, then they are inversely proportional to each other. If the number of orbit is less, then the velocity will be more. That means the electrons which are near to the nucleus, they travel with more velocity, or they move with more velocity, and an electron which is far from the nucleus, they move with less velocity. That's what you can come to know. So v and n, they are inversely proportional to each other. The velocity of electron near the nucleus travels faster, or their speed is more than the electron away from the nucleus. Like this you come to know from the expression for velocity. Now let us see the third one, that is frequency of electrons in the stationary orbit. The third one, frequency of electrons in the stationary orbits. The frequency here indicates how frequently it completes one round, the revolution, one round. How frequently it comes back to its own position, the electrons, when it revolves around the nucleus. The frequency is the number of revolutions frequency is the number of revolutions made by the electrons in 1 second. Now to find out the expression for frequency, we know that angular frequency omega is equal to velocity divided by the radius. This is the expression for angular frequency. This angular frequency, if you change it into this linear frequency, we are talking about linear frequency. You can write even small f also. Angular frequency and linear frequency relation is 2 pi omega, 2 pi nu. It is V by R. Here you can write, since omega is equal to 2 pi f or 2 pi nu. So from here, nu you can find out, that is your frequency, V divided by 2 pi R. 2 pi R. Then if you put the value of velocity, this is in equation number 2 that we derived earlier, you get the expression for linear frequency. Putting the value of V, that is equal to Z squared divided by 2NH epsilon naught, we get nu is equal to, velocity expression is Z squared divided by 2NH epsilon naught divided by 2 pi R. 2 pi R. This will give us frequency is equal to Z squared divided by 2 2s are 4 pi r n h epsilon naught. This expression will give you the expression for linear frequency. Likewise, for hydrogen atom, here also for hydrogen atom, Z when it is equal to 1 and n is equal to 1, we get the expression for linear frequency as Z, that is 1. So it will be simply E squared divided by n is also 1, so it will be 4 pi r h epsilon naught. This is for hydrogen atom, for the electron in the first orbit of hydrogen atom that revolves around the nucleus. This is the expression for linear frequency. Then the fourth thing that you have to know is about the energy of electrons in the stationary orbits. To know the energy of electrons in the stationary orbit, it will be the sum total of kinetic energy as well as potential energy. As in the starting, to derive the expression for radius, we know that centrifugal force Fc is equal to electrostatic force. With that you can start. Centrifugal force is mv squared divided by r. Electrical force is 1 by 4 pi epsilon naught z squared divided by r squared. Then you have cancelled this r. So from here what you get is mv squared. This is 1 by 4 pi epsilon naught z squared divided by r. After getting this value, mark this as equation number 1. Kinetic energy we will find out. Kinetic energy we write this K. It is equal to half of mv squared. All of you know. If you put the value of mv squared, this one here, you will get the expression for kinetic energy. Half of mv squared is 1 by 4 pi epsilon naught z squared divided by r. So it will give you the expression for kinetic energy as 1 by 8 pi epsilon naught, or z squared into 1 with z squared, you can write down together as well, into r. This is the expression for kinetic energy. That will be equation number 2. And potential energy, as you know, electrostatic potential energy. How to find out electrostatic potential energy? U is equal to 1 by 4 pi epsilon naught. Charge of electron here, negative also you have to take it. Charge of electron, charge of nucleus Ze divided by the distance, that is r. So ultimately here potential energy U is equal to minus 1 by 4 pi epsilon naught r, and on top you get Z squared. It is with negative sign. Let us mark this as equation number 3. Now if we add these two, potential kinetic energy and potential energy, then we will get the total energy of the electron in stationary orbit. Total energy of electron in the stationary orbit it will be sum of total energy. It is sum of kinetic energy plus potential energy. Kinetic energy is Z squared divided by 8 pi epsilon naught r, plus potential energy is negative minus z square divided by 4 pi epsilon naught r. This will give you minus z square divided by 8 pi. It will be 8 pi epsilon naught r. This will be your total energy of the electron in stationary orbit. If you put the value of r here, putting the value of r, that is n square h square epsilon naught divided by pi z m e square. If you put this value in this equation, the total energy of the electron in stationary orbit will be minus z squared divided by, this one minus z squared divided by 8 pi epsilon naught, 8 pi epsilon naught, and then r value is n square h square epsilon naught divided by, it will come here, pi z m e square. Pi if you cancel it out, then no other common terms, so you can write this as minus z square e square, e to the power 4 multiplied by m divided by 8 epsilon naught will be epsilon naught square n square h square. This will give you the full expression for total energy of electron in the stationary orbit. This is the expression for energy of electrons in the nth orbit. This one you can even write this n square like this into here h square 1 by n square. So you can write it separately. Now for hydrogen atom or H atom, we know that Z is equal to 1. This n we are not putting as 1 because for the first orbit n will be 1, for the second orbit n will be 2. So in terms of nth orbit, if we take Z is equal to 1, then your total energy, let me write it as E. Z is equal to 1, so it will be minus e to the power 4 m divided by 8 epsilon naught square h square into 1 by n square. And if you put all the standard values of m, e, h, epsilon naught, then the value comes out to be, putting all the standard values, E comes out to be minus 13.6 electron volt divided by n square. This one you have to remember. With this, you can draw the energy level diagram. Let us see now how to draw energy level diagram. This energy minus 13.6 electron volt is also known as ionization energy. It is for the ground state if n is equal to 1, ground state of hydrogen atom, we say. Let us draw here and see the energy level diagram. And this energy minus 13.6 electron volt, that is the energy that is required to remove the electron from its orbit in hydrogen atom. That energy we call it as ionization energy, minus 13.6 electron volt. Now energy level, let us see. Energy levels when you say graphically, you draw and show. This is for n equal to 1. This is called the ground state. Ground state of hydrogen atom. This is suppose say 0, or we cannot take it as 0. For a ground state, when you say n is equal to 1, then it will be minus 13.6 electron volt. Y-axis is representing energy of atom in electron volts. Now if n is equal to 2, for the second state n is equal to 2, suppose it is here, n is equal to 2, then what will be the energy? That one to know. Minus 13.6 divided by minus 13.6, you'll have to divide by 2 squared is 4. 4 3s are 12. 1 6 4 4s are 16. So it will be minus 3.4 electron volt of energy. That will be at n equal to 2. N is equal to 3. Then what will be the energy? Then here you put it 3 squared. 3 squared is 9. 13.6 you will divide by 9. 9 ones are 9. 4 6 9. 5s are 45. 1 0 9 ones are 9. Around 1.1. 1.5 volt minus electron volt minus 1.5 electron volt. That will be at n equal to 3. Then at n equal to 4, 4 square will be 16. This one will be n square will become 16. So 13.6 divided by 16. Cannot divide. First decimal. We put a decimal. Together we'll have to take it. 16, 48, 6, 8 was 8, 9, 10, 11, 12, 16, 9, 10, 54, 9, 10, 14, 1, 4. It will cross the number. So 8 will take. It will be 128. Then 8, 0 if you put 16, 5 times 30, 5, 6, 7, 8. 0.85 minus 0.85 electron volt at n equal to 4. Likewise, it will come closer and closer. N equal to 5. At n equal to 5, 5 square is 25. So 13.6, 25 if you divide it. Yes, 25 5 times is 125, 110, 4 times will be minus, if you look carefully, minus 0.54 electron volt. It will become lesser and it will become more and more. In minus side, we will say that it's becoming, the energy is becoming more and more as you go up, n equal to 2, n equal to 3, n equal to 4. So what we understand from here is, if an electron is in the near orbit, the first orbit, the electron has got minimum energy. Next one, this electron will have more energy. This energy of the electron will be more, this will be less. As you come closer towards the nucleus, and the energy becomes lesser and lesser. If you go away from it, the energy becomes more and more. So like that, it will go n equal to 6, n equal to 7, n equal to 8, and then it will come to n equal to 0. Sorry. The energy will become, it is approaching towards 0. And above, the energy above 0, we call it as ionized atoms. These are for ionized atoms in this region. energy below 0 will be called as ionized atom. This is how the energy levels are distributed in an atom. Again I repeat it, at n equal to 1, this is for n equal to 1, the energy will be minimum. N equal to 2, the energy will become more. N equal to 3, the energy will become more and more. As you go up, it will become more and more. Now suppose say that this expression will be required. Suppose an electron jumps from a higher energy level to lower energy level, then how we can express it? If an electron jumps, if an electron jumps from higher energy level, let us say it as N2, to lower energy level, let us say it as N1, then the expression for this total energy E will look like this: minus z square e to the power 4 m divided by 8 epsilon naught square h square. Then jumping from higher energy level to lower energy level, so E2 minus E1. First let me write down E2 minus E1. E2 minus E1. Then if you put N2 for E2, this will be N2 square. It will become like this: minus z square e to the power 4 m divided by 8 epsilon naught square h square. Then here it will become N2 square, or I'll write this 1 by N2 square. And then minus, this formula is minus, so this minus into this minus will become plus. Then it will look like this: z square e to the power 4 m 8 epsilon naught square h square 1 by n1 square. It will look like this. So the positive term, if you take first, or this E, what is this E? Then you know this is photon, energy of photon, h nu. And what is h nu? Then h nu is equal to hc divided by lambda. This one positive term, if I take first, then it will look like this: z e square m divided by 8 epsilon naught square h square. This is a constant term I have taken, this one first. Then this will be plus, and this term will become minus 1 by n1 square minus 1 by n2 square. It will look like this. Now this, if I leave here like this, 1 by lambda if I write, then this term hc I'll bring it down: z e square m divided by z square, sorry, this is z square e to the power 4 m, z square e to the power 4 m 8 epsilon naught square h square. Then this hc will come down, then h will become h cube c. This is 1 by n1 square minus 1 by n2 square. Here n2 is bigger than n1. Then this term 1 by lambda, we call it as wave number as well. This constant term we call it as Rydberg's constant, we write it as r. 1 by n1 square minus 1 by n2 square. Here n2 is larger than n1, higher energy to lower energy when it jumps, n2 to n1. You can imagine like this: from any one of the state n2 you can take to n1 when it jumps from higher to lower energy state. where 1 by lambda is called the wave number. Sorry, here one thing, z will remain. Here it will be z square. And z square is missing here. And r is called Rydberg's constant. Its value is 1.097 into 10 to the power 7 per meter. Now for hydrogen atom, if Z is equal to 1, your wave number will be Z is equal to 1, then your wave number 1 by lambda will be r times 1 by n1 square minus 1 by n2 square. So here it ends up your Bohr's theory of hydrogen atom or hydrogen like atoms, that is helium ions and lithium ions. Helium ions and lithium ions, we write like this: helium positive ion and lithium 2 positive or plus 2, you can say, ions. This theory is applicable for helium ion, lithium ion as well as hydrogen atom. Now, after knowing this energy of electrons in stationary orbit, the energy level diagram, now we will see the spectral lines. Now when we say spectra, then you are very familiar with the word spectrum, that VIBGYOR. For that what you require? We require a prism. So any spectrum you want to see, you require one prism. That light rays, like white light, when you pass through prism, then it splits up into VIBGYOR, spectrum is produced. So this spectra that we are going to study now for hydrogen, here also the rays that are emitted will have to pass through the prism, then the spectrum can be seen. And as I said already, that line spectra was observed in hydrogen atom. Line spectra, what's line spectra also I told you, it's not continuous. Continuous means one color after the other. A bundle, you will see bundle of colors. When you say spectrum, line spectra, then here you can see, then gap, then afterwards you can see another color, then gap. Like this spectra are observed in hydrogen atom. Now let us discuss about that. Sorry, one thing I missed out. This is called n equal to 1 is called the ground state of hydrogen atom, and these are called the excited states. Excited states of hydrogen atom, n equal to 2, 3, 4, 5 onwards. And one more thing, the value of R, what is the value, numerical value I have shown to you, but here R represents this one, E square m divided by 8 epsilon naught square h cube c. Here R is equal to, in the expression it is e to the power 4m divided by 8 epsilon naught square h cube c. This term we call it as Rydberg's constant. Thank you.